All right. Good morning, everybody. Today, let's continue what we started on chapter number 7, and hopefully we will get to the end of the chapter number 7 today. So, as I told you in the video that I recorded, we will have an in-class assignment today. We will do slightly different. When the time comes, I will give you the instructions for the in-class today. Okay, uh, let's see where we left off here. Okay, so that was the last slide that I showed you in the recorded lecture. So we talked about the Schrödinger model, how the Schrödinger model describes the atom. So now we are going to use the idea of probability, and we will solve the Schrödinger equation to find the probability of the electron as a function of the distance. Solving the Schrödinger equation, we will come out with 4 quantum numbers. N is the principal quantum number, it's just the number of the shell. L is the angular momentum quantum number, so that describes the subshells. And ML is the magnetic quantum number, which describes the orientation of the orbitals in the space. So therefore, it will yield the shape of the orbitals. And MS is the spin quantum number that describes the orientation of the electromagnetic moment in space. Okay. To describe an electron, we need the 4 quantum numbers, and for each electron, there is a unique set of 4 quantum numbers. And that's the idea of the Schrödinger model. Okay, so moving on today, we will start talking about the periodic table, how the elements are arranged in the periodic table, and some of the periodic properties that are important for us at this point. All right, chemists, they like to organize things, and usually organizing things involve placing things that have similar properties in the same family or in the same drawer in a box. Okay, so the first successful person to organize the elements was Mendeleev. Unfortunately for Mendeleev, he was from Russia, and at the time, not many people spoke Russian. So that's why his idea of organization of the elements took a little longer to be recognized and understood by Western scientists. But Mendeleev was genius. His organization of the elements was outstanding considering what was available at the time. His idea was that the properties of elements are the periodic function of their atomic masses. By periodic function, it means that we started from element number 1, go all the way into the row, and we come back again to the same properties of the element number one. So periodic are things that repeat themselves. So his idea here was that we start with hydrogen, go all the way to the group here, number eight. And when we come back again to lithium, the properties of lithium and hydrogen would be similar. And then again, a cycle and coming back, then again here, this element would have similar properties. By similar properties, that means similar chemical properties. And that was the starting point for the Mendeleev. Okay, so he was one of the first to have the idea of a family organized in a column. The biggest mistake of Mendeleev was to organize the elements as a function of the atomic masses. However, this was the end of the 19th century, and that was what was available to organize stuff. Okay? Uh, Mendeleev organized all the elements that were known at the time. And here in his table, that was the most amazing thing. There were some elements that were not discovered yet. However, Mendeleev predicted the masses of these elements and also predicted where they would fall in his table. Okay? So here I'm highlighting the elements with atomic masses 68 and 72. So let's see what Mendeleev predicted about these elements and what was found when these elements were finally found in nature. For the element with atomic mass 68, Mendeleev called aluminum, and later on it was found, and it is the element gallium. According to Mendeleev, the predicted mass would be 68. Gallium is 69.3, so pretty good. Mendeleev also predicted the density, 5.9, and it was found as 5.9. Mendeleev predicted the melting point. This element would have a low melting point, and gallium melts at 30 degrees. And also Mendeleev predicted that Eka aluminum will form oxides, and the formula would be 2 Eka aluminums to 3 oxygens, and that's exactly what gallium forms. And also the chloride would be 2 Eka aluminums to 6 chlorides, and that's exactly what gallium forms. Okay. So the predictions by Mendeleev were really, really impressive without even knowing about the element. And the same thing for Eka silicon, which later on was found to be the germanium. So again, prediction of atomic masses, density, melting point, even in this case here, color, which is really impressive, and boiling point, for example. So Mendeleev was capable of predicting all these properties using the idea that elements in the same column would have similar properties. And that was the starting point to organize the elements in a table. Later on, in 1913, Henri Moseley suggested to organize the periodic table not as a function of the masses, but as a function of the atomic number. Okay, and that is how we still organize the periodic table today. All right. So we talked a little bit about the periodic table early on, but here it is again. So the organization here is by atomic number. So starting with 1 for hydrogen, 2 for helium, 3, 4, and so on. Remember that the number of the column is called group. Elements in the same group will have the same number of valence electrons. Remember that valence electrons is the number of the electrons in the last shell. So we have to count the whole shell. And the number of the rows are called period. And the number of the period is exactly the number of electronic shells, which is represented by N. For example, lithium, which belongs to the group number 1 and period number 2, will have 1 valence electron and 2 uh, electronic shells. Okay, let's play a little bit here with the table. Let me switch screens. All right, so remember group is the number of the column and period is the number of the row. The group number gives you the number of valence electrons and the period number will give you the number of electron shells. Another way that people like to group the elements is that the groups 1 and 2, this group is called S block. S block because they have as the valence shell s orbitals. On the other side of the table, between groups 13 and 18, we have here the p block. So the p block, in addition to s orbitals, they also have p orbitals as the valence shell. And in between the s block and the p block, from groups number 3 all the way to 12, we have here the d block. D block elements have electrons in the d orbitals. And we have here what's called F block. F block elements have electrons in the F subshell, and they come from here. So they are squeezed right here, okay, right here and right here. So they are the lanthanides, the elements between barium and hafnium, and the actinides between radium and rutherfordium. When you do the electron configuration, you can use the off-bow principle, which follows the arrows that I showed you. But some of you like to use the trick of just looking at the periodic table and then from there getting the electron distribution. So let's get here, for example, phosphorus. Phosphorus has atomic number 15. So the trick here to get the electron configuration of the phosphorus is starting from the top and moving all the way to phosphorus and then filling the orbitals. So let's see, it's been a while that I haven't done this. So we start with the shell number one. Shell number one only has the s orbital. So hydrogen will have 1s1. Helium will have 1s2, and that's the max. Then we move on to the next line. So we started here, went here, move on to the next row right here. Now we have shell number two. We have to start with 2s, lithium 2s1, beryllium 2s2, jump from here all the way here. Now we start filling the 2p subshell, boron 2p1, carbon 2p2, nitrogen 2p3, oxygen 2p4, fluorine 2p5, neon 2p, 2p6. So we are here. Then move on to the next line, next row, sorry. We have to fill the 3s2, jump here to aluminum. That's going to be 3p1, 3p2, and 3p3. And that's how you get the electron configuration. So you move along the periodic table, filling the shells and subshells till you get to the element that you wish to do so. And then, as you can see here, the valence shell is the shell number 3, and we have 5 electrons in the valence shell, and that has to match with the group that phosphorus belongs to. And that's another way to get 2D electron configuration. Okay, let me check one thing here. All right. So now let's start talking about the periodic trends, and I will show you just the radius today, and that will be enough for today. All right. So remember that periodic trends are something that starts in the first column, has some sort of trend along the rows. And then when we come back to the first column, it resets. So for example, the moon cycles are something periodic because it repeats itself after some amount of time. So periodic trends will start in the column number 1, show a behavior, and then when you circle back, it will start over again. Starting here with radius. Radius is the most important periodic trends. All the other trends can be derived from the radius. Remember here that the radius is basically result of the interaction between a charged positive nucleus and its electron. That will determine the radius. More positive charges, the radius will shrink. Less positive charges, the radius will increase. Another thing that we have to take into account as well is the number of shells. More shells, longer the distance between nucleus and electrons, and that will decrease the interaction. So imagine a classroom where the professor is the nucleus, and then each row will represent an electron shell, and the students in the row will represent the electrons. So if we add more shells, what should happen with the radius? Of course, more shells added, the radius will increase. Therefore, the first conclusion that we get from here is that an increase in the number of shells will result in an increase of the radius. Okay, so remember about the classroom. An extra row added increases the size of the classroom. Oh well, if we move from row number 1 to row number 2, what we are basically doing is adding an extra electron shell from row number 2 to row number 3, another electron shell. Therefore, from top to bottom of a group, the radius will increase. Okay? From top to bottom of a group, the radius will increase because we are adding extra electron shells. Now here is the question. What happens with the radius if we move from left, oops, sorry, from left to right? From left to right, we are keeping the same number of electron shells. However, we are adding one extra positive charge and one extra negative charge. However, keeping in the same shell. Okay, so it's like we have more professors here in the center attracting your attention, and we have students only in one row. What would happen with the radius when we have a higher charge and electrons being placed in the same shell? When we have this situation, we are going to have more positive charges, therefore more attraction, which results in a decrease in the radius. So therefore, moving from left to right, that will decrease the radius, and vice versa. Okay, so just imagine here hydrogen. We have one proton and one electron, and the interaction here will determine the radius. This is for hydrogen. And then moving to helium, we have now two positive charges, so the attraction can be stronger, and two electrons. However, these two electrons are in the same shell. Okay? So therefore, here the interaction is stronger, which shrinks the element. Okay, so here I will show you some values for atomic radius for some elements. The unit here is picometers, which is equivalent to 10 to the minus 12 meters. So as you can see here, there is an increase from top to bottom because we are adding extra shells. And if we move from left to right, along the same row, there is a decrease in the atomic radius. So example here, starting from lithium, decreases all the way to neon. That's why we are adding extra positive charges and adding electrons to the same electron shell. Therefore, resuming the radius property or the periodic trend for the radius, it will increase from top to bottom and then from right to left. Okay, increasing from top to bottom and from right to left. And this is a periodic property because starting from hydrogen, there is a behavior going from helium, and the same behavior is observed when we reset and go from lithium to neon, sodium to argon, and so on. Therefore, one of the biggest elements is cesium. Okay? A lot of electron shells there. So therefore, low attraction between nucleus and electrons. Therefore, that uh, increases the size of the element. Okay? So for the next properties, always take into account the attraction between nucleus and electrons and its size. Smaller atoms, they attract a lot the electrons. Larger atoms, the attraction is weaker. And then we will talk about electron affinity and ionization energy in the next week. Okay, so that would be the lecture part for today. For the in-class assignment today, we will do something different. I will post the 10 questions on Canvas. So I will give you the instructions, and then you have till 1:35 to submit through Canvas. And let's see how that goes. If you have problems to locate the file on Canvas, let me know. Then I can send you via email. And I will be here available if you have any questions. Okay, so that would be it for today. I will stop my video, but I will still be here, and then I will make available right now the file on Canvas. I hope you have a good weekend, and I will see you next week.